Hello there, Mr. Sutton here with the AB Calculus 6-8 classwork solutions on motion-free response.
For this calculator-based problem, we're given a particle moving on the x-axis with a velocity given by this function, and they were nice enough to graph this function up here for us. I mean, it's a calculator question, so we could have done that on our own, but they gave us this, and they're telling us the position of our particle at time 0 is x of 0 equals 5. Awesome. First part, we want to find the acceleration of our particle at time 3. Well, acceleration is just velocity's derivative. So this is v prime of 3, which if I enter v in my calculator, I can figure out v prime on the calculator. So here I am on my calculator. I'm going to enter this v in my y equals, my y1, and then quitting out of that, we wanted v prime. Now I don't actually have to tell them what v prime looks like algebraically. Since I'm just taking the derivative at a single spot, I can just say v prime and, they kind of have to take my word for it. So we're going to do math 8 dx, and I'll do alpha trace to put my y1 in there. So I'm basically taking the derivative of the velocity function I just entered, and we wanted that at time 3. Enter. That comes out to negative 5.467. And there's no units on this one, so this one's done. For the next part of this question, we want the total distance traveled from 0 to 3. Well, that's just going to be the integral of absolute value of velocity. So we'll do integral absolute value of velocity from 0 to 3 on the calculator. So here we go, math 9, 0 to 3. And I did alpha window to pull up an absolute value from that menu. And then alpha trace for y1, dx. And this all comes out to, let's see what our total distance is. So we're adding up all the positive area underneath these this curve here. That comes out to 1.702. For this part of the problem, I want the position of a particle at time 3. I know the position at time 0. X of 0 is 5. So x of 3, using my FTC, is going to be x of 0, which is 5, plus the integral from 0 to 3 of my velocity function. So let me do that on the calculator. So plugging all that in with my velocity as y1, that comes out to a position of 5.774. For this problem, which is kind of the final boss battle of this free response question, I want to find the times between 0 and root 5 pi where the particle is farthest to the right. So I'm actually looking for the absolute max of this x of t function on the interval from 0 to radical 5 pi. So I could use the candidates test on this one. I definitely have to test the endpoints, and I'm also going to have to test out critical values, places where this velocity function equals 0. But it turns out I don't have to test all the critical values, only the ones where I'm changing from positive to negative, the local maxes. Local mins we don't really need to test, because if you're a local min, that means you're smaller than the values around you, which means you can't be the biggest value on the whole graph. So let me actually graph this out on my calculator so I can find the exact spots where we're changing positive to negative. So here's my function. I entered this in y1, and before I graph this, let me go to window, and I'm going from 0 to, let's see here, I want this to be radical 5 pi, and let me do zoom 0 so that I can get the exact graph that they've been working with here. All right, so the only two spots I really care about are right here and right here, where we're changing from positive to negative. So let's do second trace, zeros, and let's see, a little bit to the left, a little bit to the right, enter one more time. There's our first 0, and I'm going to store that value now. I'm going to quit out of here, and I'm going to store that value as alpha a, so that I can bring it back whenever I want, and I'll even write that down here. A, so this changes positive to negative is how I'm wording this, at time equals a, approximately equal to this stuff here. Let me go back now and get the other value. So let's do second trace again, zeros. And now let me move to this other positive to negative x-axis crossing. A little bit to the left, a little to the right, and one more time gives us this 3.07 and change kind of value. Quitting out of there, let me store that as, let's see, we'll do alpha b, And I'll also note on my paper that that's what B represents. Whenever I write it, I mean this number here. All right, so candidates test time. Let's do the left endpoint, x of 0. Well, they gave us that one for free. Awesome. Let's also do x of a. That's going to be x of 0, which is 5, plus the integral from 0 to a of my velocity function. Calculator time. So doing that on the calculator, I get about 5.895. And now let me do x of b. That's going to be 5 plus integral from 0 to b of velocity. And on my calculator, to save a little time, I'm just going to scroll up here, yank that input from before, and I'll just change this a to a b. Boy, I'm clever. There we go. That comes out to 5.788. I mean, you should be trying to save time on these. And then finally, we need x of radical 5 pi. So that's going to be 5 plus 0 from radical 5 pi of velocity. And plugging that in my calculator, I get this other value here of 5.752. So looking at my different candidates here, I have 5. X of a gives me a higher number. And let's see, comparing that to the other numbers here, they're all pretty close, but it looks like x of a gave me the highest number. Therefore, our particle is farthest to the right at t equals a, which is really just this value of 1.7725.
For this problem, we have a car traveling on a straight road with a velocity of 55 feet per second, and its acceleration between times 0 and 18 is given by this piecewise defined function graph here. So for the first part of the problem, we want the velocity of the car, or we want to know if the velocity of the car at t equals 0 is increasing, and why or why not. So velocity, that relates to acceleration in that the acceleration is the rate of change of velocity. So if we want to figure out if our velocity is increasing, we really need v prime to know the sign of v prime. But v prime and a, which is given by this graph here, are really the same thing. So we're really trying to find a of 2 when we find v prime of 2. So what's a of 2? Well, just looking at right up on the graph here, that's 15. And that's not really all that special, except that it's a positive number. Since our derivative of velocity is positive, that means that our velocity is increasing at time 2. For this part of the problem, they want to know at what time on the interval from 0 to 18, other than t equals 0, is the velocity of our car 55 feet per second, and why? All right, so we know that v of 0 is going to be 55. They gave us that in the problem stem here. So let's take a look at what's happening to our velocity as we keep going. So since you're given the graph of acceleration, the area under this graph represents how your velocity is changing. For example, from 0 to 6, with all this positive area, your velocity is increasing along this whole interval. So we need to figure out how much our velocity increases between 0 and 6, and then we'll figure out how much we have to keep going to offset that increase and get us back to 55. So v of 6, that's going to be v of 0, or 55, plus the integral from 0 to 6 of acceleration. So that's 55 plus, well, we have a trapezoid here. This is going to be a base of 2 plus a base of 6 over 2 times a height of 15. So then we've got, let's see, this is 4 times 15, which is 60, plus 55 brings us to 115 feet per second. So how far back do we have to go from 115 to get back to 55? Well, we essentially just added 60, so we need to have an area of negative 60 then to offset that increase. So as I look here, I'm definitely racking up some negative area. How am I going to get the exact same area that I just covered with this trapezoid? Well, how about another trapezoid? It looks like we have another trapezoid if we keep going here. Now, the original trapezoid had a base of 6, a lower base of 6. So if we go out to 12 here, that trapezoid is going to have a base of 6 and a base of 2, just like the original. It's also going to have a height of 15, albeit negative 15. So let's just add this negative trapezoid from 6 to 12 in and see what that does for us. And I have to justify my answer, so I might as well show this adding on camera here. So we have v of 12, that's 115, that was v of 6, plus the integral from 6 to 12 of my acceleration. So that's 115 plus we had a base of 2 plus a base of 6, height of 15, and then all over 2, and that's going to be negative. So we've got 115 minus 60, which gives us 55. And this happened at time equals 12. And we'll throw seconds in there just to be on the safe side with units. On this problem, we want our car's absolute maximum velocity on the interval from 0 to 18, and a justification. Since we have a closed interval, we're going to use the candidates test on this one. We're just going to test the endpoints and critical values to see which one gives us the biggest velocity. And we don't have to test all the critical values, just the ones that are local maxes. So I'll start my justification by just reminding us that acceleration is the same as v prime, and we want to know where v prime is changing from positive to negative. That'll give us the local maxes. So this only happens at time 6. We change positive to negative for our acceleration, our v prime. So that's the only critical value I really need to consider. This other one is a local min, so I don't need to consider it, and I get out of having to consider it by writing this right here, at time 6 only. Okay, so we've got our first endpoint, 0. We already know that gives us 55 for the velocity. We actually also know what happens at this critical value. We found in part B, and we wrote down that velocity at time 6 was really just 55 plus the 60 area here, so 115. So we just need to find the other endpoint at time 18. That's going to be time 6, or 115, plus the integral of acceleration from 6 to 18. So I've got 115 plus, and now I've got two shapes I have to add. I have this huge trapezoid underneath here. This is a base of 10 plus a base of 4 divided by 2 times a height of negative 15. So I guess I'm actually subtracting that. And then we've got this triangle over here that's 1/2 times a base of 2, height of 15. Adding all that up, this trapezoid has an area of, let's see here, we've got 14 over 2 is 7 times 15. That's going to be 105. So 115 minus 105, which is 10. And then we have 10 plus 15, which comes out to 25. So taking a look at these different candidates, 115 gives us is the largest velocity. So then our max velocity is going to be 115 feet per second at 6 seconds. For this last part of the problem, we want to know at what times on our interval, if any, is the car's velocity equal to 0? Justify your answer. Now the key on this one is if any. So there's at least the possibility they're opening the door for here that maybe this doesn't happen at all. To see if our car's velocity is ever 0, consider the following. We're starting with a velocity of 55. And we already know the maximum velocity is 115. But how about the minimum velocity? How low does this thing go? If we have a minimum velocity that's below 0, then maybe we start actually looking to see what time gives us that. If our minimum velocity is positive, then we're not going to bother trying to find a velocity of 0. So let's go ahead and find that absolute min. We start by considering endpoints and critical values. In this case, we only want critical values where we're changing from negative to positive for v prime. So I'm going to start by saying v prime changes negative to positive at time 16 only. This is our only critical value that's a local min. So we're only going to consider that one. We don't need to worry about velocity at time 6 because we already saw that's the absolute max. So again, we had a starting velocity of 55, an ending velocity from part C of 25. And now to find this velocity right here, we actually kind of calculated this when we were figuring out velocity at 18. It was velocity at 6, so 115, plus the integral from 6 to 16 of acceleration, which is to say 115 minus the area of this trapezoid down here, which again was 10 plus 4 over 2 times a height of 15. So we saw in part C that this was really 115 minus 105 for a total of 10. 10 is our absolute min out of these three candidates. And significantly, 10 is not negative. In fact, it is a positive number. Since the absolute min of our velocity is positive, velocity cannot be 0 anywhere on the interval from 0 to 18. For this problem, we have a particle going along a straight line, and between times 0 and 5, our velocity is given by this v of t function. And the position is given by s of t, and we know that s of 0 is 10. So for the first part of this problem, we want all the values on the interval from just 2 to 4, for which our speed is 2. All right, so first thing I'm going to do, I'm going to enter this crazy velocity function in my calculator in y1 equals. So I've done that here off camera. But now they want to know about the speed. Speed is the absolute value of velocity. So we want to graph absolute value of velocity here. So for that, I'm going to do, let's see, alpha window. That brings up abs. Press enter. And then for velocity, I'm just going to do alpha trace y1 to get that in there. So there's our speed function. We want to know specifically where our speed function has a value of 2. So I'm going to go ahead and graph the horizontal line y equals 2. I'll put that in y3. And then I'll just see where those things intersect. So let me disable my velocity function here. So I've just got speed and y equals 2. And I'm also going to go to window, and I'm going to set my interval to be from 2 to 4 so that I'm not wasting time graphing anything else. Let me do a zoom fit on this. So zoom 0. And let's see what that comes out with. So here is our speed function. It goes down, it comes up, amazing. And then here's the line y equals 2. So we just need to see what these two intersection points are. So our first intersection point, if I do second trace, intersect, I press enter once for my speed function, enter twice for y equals 2. And now this third enter, normally this is just kind of an afterthought and we just press enter. But it's going to matter where you have your spider when you press this, because it's going to give you this intersection or the other intersection depending on which one you're closer to. So I'll move over to this intersection. I want this one first, and that's going to be 3.128 and some change. If I round it off, though, that's 3.128. And now let me do the exact same thing again. So second trace, option 5, intersect. And now I'm just going to move my spider over this way and press enter 3 times over here, and I get this other intersection point of 3.473. And there we have it. On this part of the problem, they want an expression with an integral that gives the position s of t, and then use it to find the position at time 5. So we can write s of t equals s of 0, which is 10, plus the integral from 0 to, I guess it would have to be t, because that's our input variable here. So integral from 0 to t of, we want s prime, which is really just v, and we can't use t inside the integral, so I'm going to use x instead. You can't have the same variable in your limit of integration and your variable of integration. So then I've got 10 plus integral from 0 to t of v of x dx. And that'll give me my position at any t value I want. Next, to find time 5, we're going to go ahead and plug this in. So I'm going to have 10 plus the integral from 0 to 5 of v of x dx. And let me do that on the calculator now. So I've got 10 plus math 9 for integral. And then we've got 0, 5, and now my velocity function, I stored that as y1. So alpha trace y1, and then dx. And this is going to come out to, drum roll please, negative 9.207. And what are the units on this? Well, they didn't give us units, so we're not going to give them units. So just negative 9.207. On this problem, we want all the times in our interval from 0 to 5 where our particle changes direction. So we're basically asking when we have a sign change in this velocity function here. I'm going to start by writing v of t equals 0. That lets people know, hey, I'm checking out x-intercepts for this thing. And now let me go and actually graph the v function on my calculator. So here I am on the calculator, and you'll notice that I re-enabled my y1 because that's where I stored velocity, and I disabled my speed function and that horizontal line I drew for part A. Now I'm going to go to Window, and I'm going to adjust this to be from 0 to 5 for x values. And let me zoom fit this thing and see what we can get. So here's my velocity function, and we see that there is, let's see here, 1 and 2. So we've got two different places where we're crossing the x-axis here, and this is just kind of a different angle or a different window on that, but it's the same function. So let me do second trace and see where we're actually crossing. So second trace, and now I'm going to do zeros. And let's see, my left bound, I'm just going to enter it directly as 0. For my right bound, I'll just enter 2. And enter one more time. That gives us the value of 0.536. So there's one place where velocity changes sign at 0.536. And notice that I'm specifying that we change sign. I'm not just saying velocity equals 0 here. I'm saying we're changing sign specifically at this value. Because that's what you need to really show a direction change, is a sign change in velocity. Next, let's find the other 0, the other sign change spot. So second trace again, and then zeros. And now I'll directly enter the left bound 2 and a right bound of 5, just so I don't have to mess around with my spider. Enter again, and that gives us 3.318. So there's our other value. And we've proven now, because velocity changes sign here, our particle is changing directions at these times. For this last part of the problem, they want to know if the speed of our particle is increasing or decreasing at time 4. So there's a few ways to do this one. Since we actually already put the speed function in our calculator, we could calculate the derivative at time 4 just to see if that's positive or negative. Another way to do it, the way I actually ended up doing here, is to compare the signs of velocity and acceleration. So let's first find velocity at time 4. So for that, let me go to my calculator. Let me clear out my graph. And for velocity, I'm just going to do alpha trace y1. So this is where my velocity function still is. Open a parentheses and plug 4 in directly there. That comes out to negative 11.476. And that's a negative number significantly, because we have to compare the signs of this and the acceleration. Now the acceleration, this is going to be v prime of 4. And the nice thing about this is I don't actually have to write out what the derivative of velocity is up here in order to use this. I just have to take the derivative at a single spot with this function that I've already defined. So let me go back to the calculator. Let me do math 8 for derivative, dx down there. I'm going to do alpha trace to put y1 inside the derivative, and we're evaluating this at x equals 4. To get a value of negative 22.296, which is also negative. I notice that v of 4 and a of 4 have the same sign. That means that we are speeding up at time 4.